Yeah. Yeah, but did I get your homework card turned in so that I could grade it? Well, that's probably why. You're supposed to turn in your homework card. Yeah. Yeah, I mean, those of you that were gone Thursday, you probably don't have your homework card turned in. That's why I asked you to look at your grades and check them. Probably. So you're not going to turn in your homework card.
I don't know where it's at. I'm pretty sure I turned that in.
Friday you had a sub. All right, we'll look at that after when I hand those back in a minute. Okay, we don't have a lot to go over today, but we do have a few things to talk about. You had a day off on Friday. What now? Oh, all right, nobody leave. Of course, Landon walked out right when that happened. Okay, listen. Population and community are words that when we use them in our everyday lives generally mean about the same thing. When we talk about the population of Wheaton or the population of Traverse County, those basically mean the same thing as the community. Okay? But in a natural sense, these two things mean different things. Okay, a population is basically a group of the same species that kind of lives together where they can actually mate with each other. Okay, so it's a group of the same species that live and interact in an area, but kind of one of the things in ecology that we tend to look at is, can they share genes? Can they mate with each other? Oops. Can, yes. They can mate with each other. So they're able to interact, and so there is the probability, or there's a ability for those organisms to mate with each other and have offspring. And that's sort of important when we start talking about populations, because as we're going to see, the things that we're talking about is what happens to populations over generations. So a lot of this deals with evolution, as we talked about before, but we're going to look at it more from an ecological point of view. So if we were to look at a group of honeybees in, say, Oklahoma and a group of honeybees in Minnesota, we would not call them the same population, because even though they may be the exact same species, they don't really interact, they don't live near each other, and they can't mate with each other. Okay? A community, on the other hand, is all the species of organisms that live in an area. And just like population, when we're talking about a community, I mean, obviously the mating doesn't come into effect here, but we're talking about them interacting with each other. And we see the word that sticks out in both of those, or at least is similar in both of those, is interaction. And that really is kind of the definition of ecology, as we'll show in a minute. So around here we would talk about a population of pheasants that live, in the county, and they interact with each other. They're able to mate with each other. But then the community would include the plants that the pheasants eat, the predators like the fox and the coyotes that eat the pheasants, the bugs that the pheasants eat. All of those things would go in together with the community. So those are two definitions we need to get out of the way, and they kind of lead to the big definition of this chapter, ecology, which is basically the study of how living organisms interact. Okay, does anybody in here hunt coyotes? A little bit? Why?
Well, they do kill pheasants.
Okay, so you're taking into account an ecological interaction, right? Hopefully if we limit the number of coyotes, then that should increase the number of pheasants because there's not as many predators to take those out. And we see those interactions, right? But the point is, as we see populations of coyotes go up, we see the population of pheasants go down and vice versa. And so there's this relationship between those two populations because of how they interact with each other. But the same is true of food source, right? If it's a really bad winter with a whole lot of snow, the pheasant population doesn't do very good because it's hard to find food. And so that population will go down. And if the pheasant population goes down, a lot of times the coyote population goes down too because they depend on the food source. Now, obviously, coyotes have more than one food source, so it's a little bit more complex than that. But we see those interactions. As one thing changes, another thing will change because it either depends on it or its livelihood is dependent on it. I got John all riled up now. I should. I think everybody knows that John deals crack, though, so. Okay, so here we see a community of organisms living in the African savanna. We've got the plants that grow there, the animals that eat the plants. We've got the, two different organisms that eat the plants, elephants and the antelope. And then, I don't know, probably there's a lion back there somewhere, so the predator too. So all those organisms interacting together consist of the community. Okay, now when we talk about populations, so the species, right, that lives in a certain area, we can talk about certain features. So these four things are the main features that we look at when we look at the interactions of populations and how those populations survive. So first is number, and that's basically just the population size. How many pheasants are there in Traverse County? How many coyotes are there? Okay, then we look at density. And density, as the name implies, basically says how compact are the populations. There might be more of one type of organism than another, but the density of the second one might be a lot higher because they all group together, and they're all only found in one area. Okay, another feature of population is their growth. Are they increasing, decreasing, or stable? And another we can look at is the rate. How fast are they increasing or decreasing? Okay, certain types of organisms are very stable as far as their numbers go. Certain other ones are variable. They're going to increase and decrease and increase and decrease depending on the situation. A lot of that comes down to the weather and the climate. And then the fourth one is dispersion. Anybody know what dispersion would be, or have a guess?
How dispersed they are.
Okay. Can you expound on that? How dispersed they are? Okay. So if we look at how different organisms are spread out through the environment, yeah, kind of their territories or how they group together, because there's certain organisms like, say, zebras that group together, right? And there's certain organisms like wolves that tend to be more solitary. They may group up for a little bit, but for the most part, they're kind of out there on their own. They don't form big groups. And so that basically looks at population grouping. And we'll look at some specific examples in a minute. Now, all of these are things that we can talk about as far as humans go as well. We can talk about our population growth. Okay. Turns out, if you look at population growth here in the United States, it's actually fairly stable. The fact that our population is increasing actually mostly comes from immigration, people coming in. And without that, we'd actually probably be losing a little bit. So it turns out economies are kind of based on population growth. So without that, the United States economy might not be doing so good. Dispersion. So nowadays, humans tend to actually group together. If you look at the majority of the population in the United States, everybody lives in cities, and that has to do with economics, work availability, and that kind of stuff. But if we went back just 100 years, that would have been a lot different. It would have been much more spread out. Density kind of goes along with that. And then size is just, how many people are there. And so this map right here kind of shows the density of the U.S. population. And we can see, as we would expect, out here where we have big cities like Boston and New York and Baltimore all along the seacoast, we have a high population density down in Florida where we have those. California, this would be San Francisco, this would be L.A. And you can actually pick out cities based on how blue the map is. What's that? Yes, these are all counties. So you can see, looking here, Big Stone County is actually a little bit more dense than Traverse County. Traverse and Roberts, at least on this scale, are about the same. Yes, the more blue it is, the higher the density, the more towards the yellowish-white side, the lower. So you can see, if you don't like people, these would be places to move, because you'd be as far away from people as you could be, depending on where you lived. Okay. What would that be right there? Fargo, right? That doesn't make any sense, Matt. What about this one? Anybody? Sioux Falls? Okay, obviously. Twin Cities, Minneapolis, St. Paul. That one county is so big in California. I think a lot of that is desert. So like the Mojave Desert and all that, I think is all in here, and they break things up. Really, they break things up based on voting blocks, but because there's not very many people that live there, the counties out there are organized that way. Okay, anybody know what this one is? What state is it, for one? Colorado, so that would be Denver. Okay, what about this one? Salt Lake City, because that's Utah. Very, very low density. Yes. So you can see, Montana, pretty good. Wyoming, which is actually the lowest population state, we can see doesn't really have as many patches like this, but it also doesn't have as green of patches, so they're just more spread out. Even though they've got a lower population, they don't have the bigger cities like Billings and that kind of stuff. Wyoming is... Why can't I think of it now? You could ask me any other one. No. I almost had it. Chesapeake Bay, Wyoming. Yes. A landlocked state has a bay. I don't know. It'll come to me. Cheyenne. Cheyenne. There we go. I almost had it. Now, as far as growth goes, there's two different models. The first one we're going to look at is exponential growth. Okay? And yes, it would probably be a good idea to sketch this out. So, have you studied exponential growth in math yet?
Yep.
It's fun, isn't it? So, exponential growth, and a real good example of exponential growth is bacteria, right? You have one bacteria cell, it splits, you have 2. Each of those split, you have 4. And then 8. And then 16, 32, 64. So, over each generation, basically, the population doubles. And that's what we're showing right here, okay? And this is actually very close to what we've seen of the human population over the last 100 years or so. We've been in kind of an exponential growth. The human population is doubling basically every generation. Now, as it turns out, we'll learn that that can't go on forever, and in fact, about 2050, the human population of the world will, based on the people who have had kids and everything, it's already kind of been determined that the human population will level out at about 10 billion in 2050. Now, where it goes from there, we don't know. It could level off and stay there. It could keep going up. It could go down. It completely depends on how many kids people tend to have. What's that? It could after that. If all of you guys decide to, everybody your age in the world decides to have 8 or 9 kids, then yeah, it's gonna shoot up after that. So we'll talk about it. All right, now, exponential growth tends to happen when resources are unlimited. Basically, there's nothing to kind of kill off of that organism, or very few of them die. And the biggest reason that we've seen exponential growth of the human population is because of medicine. Modern medicine, I had to finish till John stopped, or I had to wait till John stopped. Okay. The human population has been growing exponentially specifically because babies don't die very much anymore. All right, just stand there. I'm nervous. I'm nervous that we're not going to get through everything we need to get through.
Yeah, he seems like a big meth kind of guy.
Kind of wonder how the drug dogs do in a chemical room, though. Kind of smells they get off of that.
Don't even go in there for that smell.
Yeah, the dogs are going crazy.
It's like when he gets out to the parking lot.
One day the dog took off and walked behind and fell down. Yeah, did you hear about that one, Mr. Roark?
What's that?
They took that dog out to the parking lot and the dog just took off running and the guy fell over.
Did a death roll right in the face. They don't do the big parking lot there with all that. Got nothing to worry about yet. No, I got Dylan like an hour. Dylan's with him. I put that pump in the road. He's got on the job. You can text him. I just got a lot of shells. I actually cleaned out all the vent shells on the floor. You should have seen it, Roark. You couldn't even see the bottom of my floor. I cleaned those out, but then yesterday they started acting up. No, not me.
Seems like a way to lose. No, use a lot of money in a short amount of time.
Well, not really. Most of the time it's just in the yard, huh?
He goes and shoots the gun and then he picks it up all and goes and dumps it later.
Well, that way I'm not leaving them out on the road.
On the road, he says.
Yeah.
Not in the
Well, yeah, that way it's safer. You just don't get out.
Yeah, shooting
Less risk of getting shot from other passengers if everyone's safe in the vehicle.
You know, you shoot the ticket pass.
Well, there's probably give or take 3 or 4 more people.
3 or 4 more cars. I had a bunch of hair.
Well, I got a battery in the back.
You know, the shells dancing off the windshield.
Oh, yeah, I got my AR order. It's in the process of being made.
I thought you were going to say that was in your pickup, but I was going to say, okay, they're going to find it.
No, they won't find it.
It's going to be like,
Oh, yeah, that's baby killer.
find an AR.
230-year-old man exploded up. Well, I'd only take down that for 60 rounds. He's a drum bag. Only 110 rounds.
Right, it's so tight you can hardly jam the shells in it.
Oh, yeah.
All right, let's go learn something.
Oh, he's ready to write down names and roast everybody.
Okay.
That's a good one or the bad one? That's the big one.
Let's go through this. So up to about, the early 1900s, life expectancy was fairly low, not because people didn't live into their 70s and 80s like they do now, but just because there were a lot of diseases that killed infants, and actually there was a lot of children that died in childbirth. And so because of that, a lot of families tended to have large numbers of children, sort of to offset the fact that they figured some of them were going to die. Some of them weren't going to make it. Now, once modern medicine kind of came in and made it so that those kids didn't die so much anymore, that's where we see this huge uptick in the population, because all these people who had been used to having all this high infant mortality kept having that many kids, and we see the population spike after that. Now, the biggest reason we're going to see this leveling off around 2050 is because people just don't have as many kids anymore, because people, well, it's going to be at that point, yeah.
What does that chart look like? Like the population growth from like 1800?
Well, we'll see that. We're going to watch a couple of videos. We won't get them today because of the interruption, but we'll see that tomorrow. We'll look at that, okay? So, because we change the environment, right, so that, and here we say resources, basically people didn't die as much, we see this exponential growth in the human population over that little bit of time. We tend to see exponential growth when the number of organisms is small compared to the resources. So, when we have bacteria, if you get a bacteria inside you, like E. coli or something like that, that's going to make you sick, we see exponential growth of that because there's a very small bacteria. There's lots of resources. Guys, there's lots of resources, and there's not a lot that is going to kill off that bacteria until your body kind of gets involved. So the beginning of getting sick, you have exponential growth of that bacterium inside you. Okay, we call this a J curve because, it looks kind of like a J, but that's exponential growth. Now, to compare that to the other main type of growth, called resource-dependent growth, in this case we see high growth at the beginning, and then it levels off. And this is what the human population is doing. So the human population now is going towards a resource-dependent growth. Time. Yeah. Which makes more sense than tire. Okay. Now the carrying capacity, that line up there for natural populations, is the number that the environment can support. And so the human population doesn't model this perfectly because we're not reaching a carrying capacity. We may someday. I don't know what the carrying capacity would be for the Earth. It would be more than 10 billion people. It's going to be dependent basically on how much food we can grow. As far as, places where we can live, we got plenty of that. It's how much food can we grow. That's going to determine the carrying capacity of the human population on the Earth. For other organisms, that carrying capacity could be dependent on food, and a lot of times it is. It could be dependent on predators. Okay. For certain populations, they're going to be limited for how many can live in a certain area based on how many predators there are around. We call this an S curve because it looks like an S, but we see the leveling off of that population when it nears the carrying capacity.
What about water? That could be a problem.
It can be in certain populations, but I would say not. The reason I would say that water is not going to be a limit to the human population is because as more water becomes, there's plenty of water on the Earth, it's just salty. As more, the population blossoms, there's going to be more money put into desalinating. And really the only reason we don't take water from the ocean all the time is just because it's expensive to do. But at some point, it's going to be cost effective. So.
Well, and if it was really a crisis, I think people just would not care,
right? Right. All right, let's look at the different dispersions, and then we'll be done. We'll have to watch the videos tomorrow. There's three main different types of dispersions. Okay, there's random, clumped, and uniform. So if we look through an environment and we see there's really no rhyme or reason to where we find organisms, they're just kind of all over the place, that would indicate a random dispersion. And so we see the dandelions out here. There's some that grow in little clumps. There's others that are far spread. There's really no uniformity to it at all. Okay, herd animals, on the other hand, and I would say humans as well, are going to tend towards a clumped, at least right now, are going to tend towards a clump dispersion. Now, that doesn't mean that every single organism lives right next to each other, but they tend to. There might be a couple of stray ones out there, right? And when we look at humans, yeah, there's some of us that live out here in the sticks. But for the most part, humans tend to live, at least in the U.S., in a clump dispersion. And then there's uniform. Uniform is where we kind of have the same amount of space in between organisms. This one's a little bit more rare. We see penguins like this. Birds actually tend to live, a lot of birds tend to live in a uniform dispersion. If you look at songbirds, they will tend to stake out territories, and they may move around in those territories, but if you kind of look at the size of the territories, they all tend to be about the same size. So they're more of a uniform dispersion. And this basically shows the same thing. So what would this one be? Clumped and random. All right. There's your question of the day.